Okay, thanks for the introduction, and it's great to be here at InterSpeech, and even if in this difficult situation, the conference is happening partially like physically, which I think is great, and it's great work from the organizers that they did manage to make it work this year. For me, it's quite exciting actually to be at InterSpeech like after so many years where I was actually working different areas than speech recognition, and it's really cool to see all this development, and that the research community is still as large as it is. My talk today will be about language modeling because that was the topic that I actually started working on when I was beginning my research career, and I think it's very exciting topic with many unsolved problems, and I will try to explain why I actually think so, what is actually interesting about language modeling, and why it can be seen as a artificial intelligence problem. So the outline of the talk is basically these four parts. First will be just motivational, to explain what are the connections between language modeling and the AI research. Then, as we already all know, neural networks became very successful over the last decade for language modeling. So I will go over some basic reasons why they are actually successful, and further I will also discuss what they are actually not so good at the moment, and what we can be aiming to improve in the future, which will be the third part. And finally, I will also talk about complex systems in the end, which I think can give us some interesting ideas how we can possibly build more advanced models in the future. Well, so the very basic question that many of you may have is why is actually language modeling an AI problem? Because language modeling is about this prediction of the next word. For a long time, it was just considered that n-gram statistics is just pretty much the best way you can go if you have large data sets. And why would actually anyone think that n-grams, which are complete trivial statistical technique, have anything to do with artificial intelligence? So, well, there are actually quite a few people who did think that language modeling is AI complete problem. The first one who was actually making some interesting comments about n-grams was Claude Shannon, at least from my point of view, from the papers that I've did read. Very actually speculated that n-grams with infinite amounts of data and infinite n would actually be able to capture any regularity in the data. So in fact, if you have a huge amounts of data, they may be actually pretty good for modeling language. Again, he was doing it in the mid of the previous century, so it wasn't really known back then how far can you go with large data sets. And then another person that influenced quite a bit me in the beginning was Ray Solomonov, who had this concept of algorithmic probability, which is a generalization of what was discovered actually later, the Kolmogorov complexity, with different names like minimum description length. That also is very much connected to language modeling, because optimal language model is actually pretty much doing the same job as if you want to compute the minimum description length. Many people that actually observed this in the data compression community. Some of them were, for example, Marcus Otter and Matt Mahoney, who did even organize a data compression prize, which was about where the goal was to develop the best possible language model for Wikipedia and to compress it as much as possible. And the prize, I think, is still going. And not surprisingly, the best entries they are combinations of n-grams and recurrent neural language models these days. Well, for further explanation, what some people Solomonov, for example, did think when they were working on these concepts like algorithmic probability, was that it can actually help in the future, for example, scientists in doing their work by being basically some sort of assistant. So some motivational examples are that if you have question answering problems, you can actually solve possibly many of them if you would be able to build some sort of perfect language model, where actually the word perfect is of course not achievable if you really think that perfect language model is the one that is basically equal to the one that would give you the minimum description length of the data, then we know that that's not computable. So we can't actually think that we can actually build really the perfect language model, but we can at least try to get as close as possible. So if we would have like this really good language model, then we can, for example, compute what is the most likely word following context the capital city of Czech is, and there actually a good language model should tell you that the most likely word given this history is Prague, because if it's trained on like some good quality data, like say English Wikipedia, then this should be the answer. But of course it goes even further. Like you can think of a language model that, for example, recommend you movies. It can even have some context. You can ask a language model to continue a sentence. For example, like a good scientist trying to improve speech recognizers would investigate in 2020 this technique or whatever, and you would actually let the language model to finish the sentence and tell you what you should be looking at. Of course, this sounds like science fiction, but it was science fiction when people were using just engrams. It wouldn't really work well for you, but these days, as we are training bigger and bigger language models, and that's actually what has been happening in the last few years, that the largest models that are being published these days are trained on like a significant part of what can be found on the whole internet, some huge neural networks. Then you can actually even try to complete sentences of this type and expect that in many cases you can get reasonable like answers. So I think that the claim that general AI can be based on language model is like very speculative, but still, because this language model doesn't have any intention, any motivation, it's just basically trying to find the most likely continuation of the sentence while keeping all the regularities that it has trained, that it has learned on the training data. So I think that this vision of general AI being based on language model is like not very clear, but still I think it's exciting to the point that we can think of some intelligent chatbots. If you would train them on conversations, then they should be able to at least like entertain people, or maybe even like help researchers when they are trying to find some answers to some difficult topics that require them to read, for example, many books, which is something that language model can do quickly, and for people it's much more difficult. So just to show you that these ideas might have been like total science fiction like some 15 years ago when I started thinking of these topics, but I did see, for example, like many examples in the last few years, how actually the text generated from some of the largest neural language models today look like. So you can just see that the red part is actually what was typed by a human who basically said some story about like some fictional conversation between Alan Turing and Claude Shannon. And then in the black is actually what was generated from the language model. And if you would actually go over it, then you can see that it actually sort of makes sense, and it's not like totally like meaningless. And you know, like the length of the context that these models can already remember is quite impressive already. Like it's much more than just a sentence or a couple of words, as would be in the case of like the engram models. So how did we actually get to this point that neural language models are so successful, and what should we do to develop even better models? Because even if we see all these impressive results, there are still work in front of us. The largest models today are trained on like orders of magnitude more data than a human can see in a whole lifetime. So certainly the training is much less efficient, and still even the best models today make trivial errors that in many cases even children would actually see. So there's still some room for improvement, but to understand what could we do in the future, I think it's good to look into the past, what we did before, and what were actually the main ideas. So when I actually started working on language modeling, my first idea was actually that to beat engrams, we should share parameters between similar contexts, and similar contexts are the one that generate similar probability. It was very simple, and I remember that I could implement this in a few days, like some ad hoc model that could share context, and I did get some 6% reduction of perplexity. I was very excited about it, and that's actually when I started working on my master's thesis here at the Speech at Fit group in Brno. and just to explain how is it connected to the neural networks. That's actually what they do. Neural networks are actually sharing parameters among similar words and among similar contexts. So I was naturally interested in expanding my idea to be less ad hoc, and I started studying n-grams. I did find that actually many scientists over the decades did find n-grams to be surprisingly hard to beat on large data sets. It's actually quite easy to get better perplexity on small data, but as you increase the size of the training set, basically the improvements were getting smaller and smaller. Even if it was known that n-grams cannot capture longer contexts, they cannot form word classes, basically the more data you used, the less improvement you could obtain. There was this very interesting technical report from Joshua Goodman in 2001, where he was just showing what I just said. If you would look at the improvement that he's getting over 5-gram model, it's basically decreasing with the size of the training set quite a bit. So just I will leave this graph here for a while. Maybe I can point at something. The Nethernet 5-gram is basically this this line. Oh, no, it's not gonna work. Sorry. Yeah, this is just a graph that's showing that humans can basically learn much faster compared to n-grams when it comes to the amount of training data. So there's definitely something that we can do better. And the neural networks can cluster the histories and the words, as I was saying. Then it's interesting to note that at the speech recognition at Brno, we were actually making progress with in deep learning actually quite a bit sooner than the machine learning community. So this is an example of Peter Schwartz's result in 2006 when he was using actually deep neural networks to improve phoneme recognizers. You can see that with a couple of hidden layers, he was getting quite a bit better results than just with single hidden layer. And there was František Gräzel, who was also using deep neural networks with 3 or 4 hidden layers. He could beat the PLP features, which was very impressive at the time. And then finally, I was also working on the deep neural networks, where actually the recurrent neural network can be seen as a deep model, because it goes over several nonlinearities before it computes the prediction. So we had actually quite a nice history of deep learning results in Brno here, much before actually the deep learning name itself became popular in the machine learning community. Here's a graph that's showing how the perplexity improved over the years on the Penn-Treebank dataset, which was kind of like a standard benchmark for many language modeling groups. And you can see that actually the neural networks did improve the state of the art like in a dramatic way. You can see that there was this huge drop in perplexity around that year 2010, where actually the neural networks became much better understood than before. And then there was this time when actually there was this incremental continuation of these results, where people were improving over these results with further scaling up to larger sizes of the hidden layers, to more hidden layers, and more advanced architectures of neural networks like LSTMs, GRUs, and so on. It was also very interesting for me as a researcher, because I would say that there was something that I would call dark age for language models. Before 2010, it was actually quite difficult to even find some interesting papers at the conferences. So mostly people would rehash ideas about smoothing techniques, class-based models, and topic models or cache models. And there was not much novelty, and there was very few research groups working on these topics. But after neural networks became successful, and there was this kind of like hope that we can actually do better than n-grams. There was like this boom where actually the NLP community did figure out that actually neural networks are great, and suddenly there was much more papers published, so that was quite exciting time. For me personally, there were like a few events where I was still like not completely sure that neural networks can beat n-grams on large data sets, and some of these results that I was able to compute it convinced me. One of them is shown here, which is basically showing if you have an n-gram model, how its performance improves over as you are increasing the size of the training set, and the same shown for neural network that is tuned for the best performance, which means that as you are increasing amount of training data, you also have to increase the size of the hidden layer to get as good perplexity as possible. So this was actually very exciting because this is the opposite of what Joshua Goodman was showing. So instead of seeing this drop in gains, as you are increasing amount of training data, this is exactly the opposite. You actually see that the more data you use, the bigger gain you get from neural nets. The gap was increasing. These neural networks basically could learn more and more with more data. So I think that was one of the main results for myself, where I started believing that neural networks can really replace n-gram models. The other one was when I actually tried to use large-scale setup that was used by IBM. It was like very well tuned for some speech recognition of meetings, I think. And here basically the graphs are showing that as you are increasing the hidden layer size of neural networks, you basically get like larger and larger improvements. And I even didn't manage to get to optimal point. Clearly from the graphs, it's obvious that if I could train even bigger models, then the improvements would be even larger than they already were. So that was also exciting. The conclusion is simple. You should use as large neural networks and as much training data as possible. Today it may seem like very obvious, like everybody already knows this, but 10 years ago when I was publishing these ideas at conferences like Interspeech, it was not this clear. Actually, some people didn't even believe that you should keep the size of the hidden layer constant, even with more data, because they can express exponentially many configurations, like with the respect to the hidden layer size. So just to explain from my point of view why the neural networks are so successful, I'd say that the key concept to understand is the distributed representations, that you can have something like class-based models, but it's not just about clustering words, where you would assign each word to a single cluster. It's simpler actually when it comes to the assumptions. You just assume that words can be members of any number of classes, and you are not even clustering just the words themselves, but whole contexts. Then feed-forward networks and recurrent networks do this slightly differently, but of course we have some new architectures like LSTMs and then transformers, but really the key concept here, why we could beat the n-gram models, is because we have the distributed representations and we are sharing parameters among similar histories, so we learn actually much more from the same amount of training data. I also do think that the simplicity of neural networks is one of the reasons why they actually work so well. Like, if you think of it, it's maybe a bit like philosophical, but say in physics, scientists are trying over the hundreds of years to develop the simplest possible equations or shortest possible equations that would describe as many phenomena in the universe as possible. And I think that in this case, it's a bit like similar, like neural networks are like trying to be, or like the neural language models are like simple when it comes to the number of assumptions. You don't even like consider that there are some sentences. You just treat the data as some sequence of symbols, and you can actually use the neural language models to model any kind of sequential data. You can use it for music, or you can use it for like any kind of sequential data with, say, discrete tokens without any change. So I think that this generality is one of the reasons why these models work so well. And I think that if we want to make further steps, we should be thinking about models that can model more irregularities in the data while actually keeping them as simple as possible. So if I would make some conclusion of this kind of like historical summary, then I would say that what worked from my point of view, like publishing the open source code, which allowed many actually groups to use neural net language models quite easily. I did actually publish the RNNLM toolkit in like 2010. I think that was a great help because otherwise many groups would not try to work on something like this if it would not be easily reproducible. And then the available data set, which was kind of painful when I was a student. I couldn't actually find data sets very easily. There was a lot of issues with the copyrights, and I think that these days it's actually much easier because there are many open benchmarks. So I think that's what worked, and that's good. Also, like sometimes people think when we are discussing these like past stories that the research community should have worked more on the neural networks. Well, I think that's a good conclusion, but maybe we can make even a better one. I think actually that the research community at any point should actually be focusing on working more on the novel ideas. I think that there's this danger that it's very easy to actually take just whatever currently works the best and slightly modify it, or take the model and just train it on slightly different data. And that leads to these incremental changes that actually do not really matter. Like if you would look from a current point of view, what is like the usefulness of all the modifications of smoothing techniques that were developed, say, 20 years ago? I would say that the techniques like nether smoothing are great, but then there was like dozens of papers that were just doing some very, very slight modifications that sometimes would give you like 1% improvement in perplexity. It doesn't matter today at all. So I think that the research community should also like have some ambitions to try to work on topics that currently don't work yet, and that at least are different from the current mainstream research, with the hope that maybe some of these new different ideas can in the distant future be actually the new state of the art. So I think that keeping diversity, the research community is not easy. Interestingly, I would say that Interspeech was actually a good conference for me because with the high acceptance rate, like I think it used to be around 60%, that in my opinion also like helped to get some of the results published when it was not clear yet that this will be useful at any time in the future, because I remember some of the reviews of my work back then were like claiming that it's all like very nice with the neural networks, but if you will use more training data, it will be so slow that it will be so impractical that it will never be actually useful for anything. Well, it turned out to be wrong, but I think it was like valid criticism, and if the acceptance rate was like 20% or less, then maybe I would not just be able to publish these papers at all. So what is difficult actually to learn for neural language models? So I was trying to like quickly explain the main ideas that they can cluster words and histories, and I guess that many of you already know that, so nothing new there. But when it comes to discussing what is actually difficult to learn for neural networks, that itself gets that's kind of difficult. We can think of the problem of the memory. It's kind of like one thing to consider as the weakness of the current models. If you would consider recurrent architectures, they have some sort of like a short-term memory, but nothing like episodic memory. Like all the memory is stored in the weights of the neural networks, and the recurrent architectures have also like a memory that is stored in the activations of the hidden layers, but that's pretty much it. So there's nothing like episodic memory, and actually we can make even like some quite specific tests that would show how neural networks fail at remembering some particular information for like a longer time. And then there's a lot of like other names for like this like transfer learning or incremental learning or composition learning, where we assume that we would train the neural network to, for example, do well on some like well-defined task, and then we make the task a bit harder and expect that that we can retrain the neural network kind of quickly with few examples, and it should work with humans. Why it doesn't happen to be the case with neural networks? You can, for example, train a neural language model to solve tasks like remembering some sentence and repeating it, and then you start testing this model on, like, say, longer sequences than it was trained on, and it will just totally fail, because the way how the neural networks learn is quite a bit different from, like, the human learning. They much more memorize the examples than people do. So I think that it's not that easy to explain, but actually a lot of researchers in the machine learning community are thinking about topics like this. Of course, like lifelong learning, continual learning, that's a related topic where you would actually assume that similarly, like humans don't have actually some training phase and test phase, but we basically process the data and adapt our whole life. There's no distinction between training and testing. It's still basically the same phase that we are in. Then if we would want to develop models that can do the same, then how would we actually do it with neural networks that typically, as they are being used in production, have all the weights frozen? Here's actually a continuation of that story that I did find on Twitter that I said was looking really so good. And you can actually see that if you would continue generating the story further, then it actually becomes worse. So you can see that, for example, in this story between where there's a conversation between Turing and Shannon, there's suddenly like Hermione talking about magic, and then there's Hagrid that is doing something whatever. So like basically that's the memory issue that I was talking about. Like even if we did make progress over the years with how many words can the neural language models going to remember with the transformer architectures, it's quite a bit easier. But still, there's this case that there's actually no kind of like intent of these neural networks to solve any task. They are just trying to predict the most probable continuation of the sequence that they are currently processing, and that's it. So you can have like these twists when they just go completely like crazy and just change the topics to something else. So again, like for the memory, I think that the memory itself, as I was talking about, it's a very difficult topic to even like define, because I think that the memory in humans has many components, and it's just easy to say that there's a memory issue in neural networks. But if we would talk about humans, we have like the short-term memory and episodic memory and long-term memory, and I think that people in psychology distinguish maybe 5 or 6 types of memories in humans, and some of them, when they get damaged, then the people still can work somewhat or live, but they have like different kind of issues. And now if we talk about the neural networks and with memory issues, just identifying what they are doing wrong can be quite difficult. One of the concepts that I was actually interested in, which is probably like easy to explain, is that with typical neural language models, you have fixed size for this short-term memory. Like if you have recurrent models, you have some hidden layers, say with 100 hidden units, then you will have like 100 float numbers that represent the short-term memory, and that's it. But for some tasks, you would actually expect that the size of the memory should grow, so that the model actually keeps learning more and more, and it can be expanding the size of its memory. So how would we actually do it? We were thinking about like more like a proof of concept, like what would be the simplest model that can actually learn to use memory, where actually memory is some kind of like a mental tool that the neural network can learn to operate with, and has this ability to expand itself. So the simplest structures in computer science that have this non-fixed capacity are like stacks. So we did work on recurrent neural networks, where actually the recurrence is through stacks, not through hidden layers anymore. So the hidden layer only like decides on what action will be done, using the stack, where the action is basically softmax over like the push, pop, and no operation. So there are like three things that three actions that the neural network can be doing with its memory. And then the memory basically is like either pushing some element on the top, or it's popping the element out, or it's doing no operation. And of course, like the neural network does not need to have just a single stack. In our experiment, we were using something like 10 stacks. So the neural network will learn to operate some number of stacks to solve some problems. And again, this was more like to show that there are problems that can be learned using machine learning, but that cannot be learned with the traditional neural networks. So here are like examples of the tasks like sequence memorization, where you would have one sequence repeated twice. You can really see it as a language modeling problem, because you can generate data of this sort, or it can be even sentences from some language. It doesn't have to be just pure memorization. It can be like a sentence in English followed by its translation to, say, French. Then you would get like a machine translation system for free. I even tried to do it in like 2012, and later it was called like the sequence to sequence model, but it was working up to some point. But the issue was with generalization with normal language models. They would just be working well on the examples that they were trained on, but when you start testing them on out of the distribution examples, like longer examples, then they would just fail. And then we had some fancy binary addition that I will not really discuss in detail, which was basically just, again, like a language modeling problem, but you would see some like sequences where we have like two sequences that get added together, like binary sequences, and you have to do actually quite a bit more work than in the memorization. So what did we find was that, that with the stacks, we could actually solve kind of this problem of memorization. So we were training on sequences of length up to 10, and then we are testing on longer sequences. That's the n on the x-axis, and you can see that we could like really see that what has been learned on short sequences that really like transfer to longer sequences. So the network kind of learned the algorithm for memorization, and it did work even somewhat well for this binary addition. Well, not surprisingly, normal RNNs and LSTMs didn't really generalize much, so they just worked well on what they were trained on, with LSTM actually being somewhat better than RNN, but these models really like memorized the training examples and didn't generalize to out of the distribution examples. So again, like I would say these things that we described in a paper in 2015, more like as a proof of concept. There's a lot of practical difficulties with the stacks. If you see them as a memory, if humans would have stacks as their long-term memory, then we would have to cycle step by step by going through the whole stack. So if you would want to remember what you were doing 5 years ago, you would have to stop and think for like a couple of hours, which of course doesn't make sense. So I would see these experiments more or less like showing that there are difficult things to learn, but that can be actually learned. Also, like sometimes when I see like these language models used like for generating text, and when actually media take these examples while being too maybe naive, there's a lot of like stories how the computers are getting intelligent already, and that computer said this, or computer generated some story, or did write this book, and it's making some claims, and what did the computer think by that particular sentence? Well, I would still say that language models still today are just basically copying sentences from the training set, and even if some of these sentences will be that I am intelligent computer or whatever, it's basically just if you would make a program of this type and believe that it's intelligent. So even if there are sometimes like these talks, especially from some startups from Silicon Valley that claim that they only have the AGI based on language models, then I would just say that that's very much overhyped. So there's often like people just either underestimate the language models or like overestimate their abilities. It's very easy. So I'd say that we are at a point where the models that we have are much better than it used to be, and we can even like solve some tasks like this question answering up to some point that I was showing in the beginning. We can be doing grammar correction and maybe even change the style of text and some fancy things of this sort, but we are still like very far from intelligent language models because the models that we have today don't even remember like things very well, and just by seeing how many groups they try to build chatbots built around new language models, and pretty much all of them failed. It's kind of clear that we still need to make some advancements. So we can, of course, speculate what are the next steps to do in language modeling, what should we be focusing on to make the progress. So I already mentioned the memory. Also, I think that the role of supervision is overstated. Should be thinking of less supervised learning, or even unsupervised development, maybe of the models, where actually the model can keep getting more and more complex without having access to some external supervision that is actually telling the model exactly what it should be doing in what context, which actually is exactly what stochastic gradient descent requires. And then I have this comment about the growth of complexity, which I'll be talking about for the rest of the talk, because I think that humans can actually grow in complexity. Like, we can learn more and more words, ideas. We can be expanding our knowledge in our brains, and we do this often in a very unsupervised way. We can even think for ourselves without any external inputs, and we can still be creating new ideas in our heads and do this potentially in an unlimited way, and that's what the current models cannot do. And the question is, which models could possibly model this type of phenomenon? Which models can we try to work on that can actually get complex, more complex over time on their own? And this is actually studied in the area of complex systems, which actually, despite the name, are often quite simple. So some possible definition of complex systems is that it's usually some simple models where actually a lot of complexity emerges kind of on its own by iteratively applying some function again and again. So it actually sounds a bit like recurrent networks, but as we will see, there are some interesting differences. Well, some examples of complex systems can be really like life, for example, or the language, where we can see this complexification over time, and even the universe itself can be seen as complex system. Actually, this area of complex systems was originally studied by physicists, so that's sort of saying where these ideas are coming from. So again, there are many examples, the universe kind of self-organizes itself over time, and it actually does, from some point of view, increase in complexity because we are part of the universe, and assuming that there was no life, for example, on Earth a couple of billions of years ago, then in some sense things are possibly getting more complex. Well, that sounds very philosophical, that's clear, but how can we actually do it, and how can we connect this to AI that we are talking about? Well, I think that if we can actually build these ever-evolving systems where the complexity increases, that would be kind of artificially evolving systems that can be actually the basis for a new generation of language models. One can see it as kind of some mathematical simulations of artificial universes or artificial life, but I think that all these concepts can be applied to language as well. We can see language as a complex system that has potential to evolve over time just on its own. Now, to get more concrete, also I must say that many basic questions in the area of complex systems are still unsolved problems. Then we can think of what actually is complex. Here are some visualizations. You can think of some checkerboard, which intuitively we would say it's quite simple because we can describe it very simply, and it doesn't seem to be getting any more complex anytime soon, right? If you would imagine that it would be 100 times bigger, it would be still the checkerboard and nothing interesting is happening there. Then you have some simple fractal, which already is looking better or more complex, but still not very interesting. And then you have quite a bit more complicated fractal on the right, which maybe already seems to be sort of generating complexity. And how can we actually measure this complexity more formally? So people did think of using, for example, this minimum description length, also known as Kolmogorov complexity, which is basically the length of the shortest program that generates the pattern that we did see. Well, it's formal, it's well known, but it's not computable. Even the approximations are actually often meaningless, and it's interesting also to notice that that the minimum description length for all these patterns would be not that much different, because even fractals can be that look complex to our eyes can often be generated by actually short programs. So the other approach that may be possible is that we can actually try to measure something like a amount of information in these complex systems. So the ones that actually seem to be increasing in complexity, there should be some increase of amount of information. Well, if we work with deterministic systems, then actually the amount of information can either stay the same or it can decrease, but it can never increase. So that's also like somewhat counterintuitive. So just to make it short, there was quite a few metrics that were proposed, for example, by Murray Gell-Mann in his book, The Quark and the Jaguar. For those of you who don't know him, he's like a physicist who did actually discover the quarks, and later in his career he did start Santa Fe Institute that actually was focusing on these questions like what is the complexity and similar. So there's no like a great way how to measure complexity, but I will show in the end what are the approaches that we try to develop at the Czech Technical University. So that here's another like example that's well known. That's like Wolfram's 1D servo automata, where there's the time on the y-axis. You start basically with a tape, one-dimensional tape where everything is set to 0, and there's just one element set to 1. And that's the middle one. That's the black square on top. And then you just iteratively apply the same rules that are shown on the top based on the configuration of a cell and its neighbors. You just compute the next state of each cell on the tape, and you just do it again and again. And what was interesting about these automata is that you can get quite complex looking shapes, even if you start with some very simple, trivial like starting state and very simple rule table. So Wolfram tried to come up with some classification. There's the maybe least interesting example shown on top left, where actually basically all the information gets erased. So some automata behave this way. Some automata are like too regular to be considered interesting, but some shown on the bottom left seem to be generating some sort of patterns over time, some sort of like structure. And that's the ones that Wolfram that consider like complex. And finally, on bottom right, it's shown like the automata that were considered chaotic. So the patterns are created and erased very, very quickly together. So it's more like looking like white noise. And it's speculated that it is not complex because we can't actually see any structure in it, but there's actually no mathematical proof for it yet. Another famous example is the game of life. I guess most of you did see it at some point. And again, like it's about the emergence of complexity, emergence of patterns. You start with very simple rule table in the beginning and some simple starting state, and just by iteratively applying this again and again, you can get like these complex looking shapes that move across the space. And it did actually catch attention of many people because it may be similar to like how complexity evolved in our universe. Actually, I can also say, just going back, because we are talking about neural networks for the first half of the talk. The interesting thing is that you can see even like these game of life and similar automata as recurrent convolution networks with stepwise activation functions. So it's actually all connected together. Then what we tried actually to do is to sample a lot of automata and find the ones that will behave interestingly. If you just do the random sampling of 2 or 3 or 4 state automata, you will not really find much anything interesting, but we defined some complexity metrics. Here we wanted to maximize the amount of patterns that emerge and stay basically in the system for a longer time. So I will not really go into the details, but automatically we could find automata of this sort that also exhibit similar properties to game of life, but game of life was defined manually. In our case, we just did score the 2D automata and using our complexity metric, and did show here the ones that increase in complexity the fastest. There's also like other approach where we used more like mathematical motivation to measure how long does it take on average for a system before it ends up in a loop, because these systems are deterministic. They always have to end up in a loop. So just quickly I will go to the end, like what are the systems that we could find. There are again like some different classes, and these are the ones that take basically polynomial time before they start looping. And again, like automatically we could construct many of these interesting automata where actually, again, like you can be wondering what is this good for like these language modeling topics. Well, I think that if you want to have models that keep doing something on their own, that can create structures and patterns without having to rely on some stochastic gradient descent and some training examples, that this might be actually the way, if we carefully design neural networks in some specific way that we describe in these papers, we can start observing this emergence of structures that can go more and more complex over time. So of course it's like speculation, but I think this can be interesting if you want to develop language models that can be trained to represent some language, but also like get more complex over time without having to rely on supervision. And that can be, for example, useful for like chatbots that can form the memory in the form of these structures that appear in these systems and are persistent, so they don't disappear from the state of the system right away. So, so for the next steps, of course, like we don't really aim to develop some like artificial universe that just keeps evolving on its own. So we would like to limit these models or like guide these models so that some structures that are actually doing something externally useful can be like promoted to be part of the future system. So kind of like to guide the evolution of these systems so that they evolve in such a way that is useful for us. So again, like instead of aiming to have artificial universe that is evolving, we would want to have, for example, like a system that represents language, but also like keeps evolving over time. And just to have a final conclusion, well, it would be great to like advance to language modeling more like in this AI-ish direction. Well, of course, like one obvious way what could be done is what already everybody is doing, to just have bigger models and more data and so on, which I think is going to happen anyways. But I think there's also like space for basic research, and we can be thinking about like these questions, like how can we design models that can learn just from the input signals without having any kind of like supervision, without even self-supervision is still basically giving supervision to the models in the form of gradients. So what could be the basis of learning or developing mechanisms that would not rely on gradients, and what could be possible mathematical models that can learn, develop, or evolve over time, even when there are no inputs. The models that I was showing are actually capable of this. Typical neural networks, if you don't show them any inputs, well, they will not really do much, anything at all. They will not change. So I think that we should be thinking about like what mathematical models can do these things, and how can we develop these like new type of models. So that's it, and we can go to the questions part.
So we have about 10 minutes actually for questions. I don't know if there is something here. Mark, maybe you can actually monitor those which are remote. Do we start with some questions? So we have Hirek here.
It works. Yeah, I just want to add a few sentences. And it's not a question, Tom, but it's a story of the late Fred Jelinek. In his last talk, a few days before he passed away in September 2010, he was asked about n-grams. He said, well, n-grams has been around for a long time, but they don't seem to evolve at all. But he said, but there is this young man who's working on something new. He didn't remember the name, which is a neural net. And I swear I have the recording of that. If somebody's interested, I can show it away. Hats off to a vision of Fred Jelinek.
Mark, do you want to go with one question from?
Yep, so there's a number of questions I've got here, but I'll take the first one from Ken Church. It's sort of a comment, and built into it, I'll sort of add a question. The criticism about smoothing is a bit harsh, given hacks like unc, etc. This means that models that back off to subwords, which rarely predict OOVs, don't give you a fair contrast when using fixed vocabulary language models that basically ignore OOVs. I guess this really comes back to the question of what do you think an appropriate way of assessing the performance of a language model is? Do you think perplexity is good enough if we're trying to, for example, generate Shannon-Turing chats?
Well, yeah, I think that the perplexity is like often discussed topic because it has some advantages and disadvantages. I would say the advantage is that perplexity is basically directly related to entropy, and that basically like connects all this language modeling to these topics that I was discussing in the beginning, like minimum description length and so on. So I would say it's theoretically well motivated. On the other hand, just by trying to optimize perplexity also like leads to this race for like ever like bigger models where like we are maybe optimizing something else than sort of like this intelligence of the models, because we keep some fixed test set and have no restrictions, for example, about the training data, then the best models will be basically the ones that also already contain the test data, and the bigger training set you use, there's the larger likelihood that you will also like contain parts of test data in the training data. I think it's already happening now in the NLP community that is using unrestricted language models that have been trained on like huge amounts of data from internet, that there's like a possibly large overlap between the tasks that people are solving and what the models that they are using have been pre-trained on. So I think that the perplexity has these issues. There's other like approach where we can actually measure more like say like task-oriented function of these language models, or possibly even like have like agents producing some language like chatbots that will be accomplishing some tasks, and that's what I also like described in some paper like a couple of years ago, that can be a possible replacement for perplexity, that we can actually start defining some tasks and then see which models can actually perform these tasks. But I think it's a very difficult issue, because perplexity has been around for a long time. It actually makes sense, but in the end you can often get a larger perplexity reduction by doing something completely else than developing new architecture of a model that can learn more patterns.
Thanks. Do you want to ask a question from the hall?
Yeah, I think we have actually here. Do we?
I can ask one from online if you want.
Okay, Mark, yeah, go on. There are many actually online here.
Okay. Could you, a question from Jesus Andreas Ferrer, could you elaborate on your ideas of language models without supervisions? Do you imply that the model will talk to itself based on the limited data that it has seen, and how would it improve the generalization?
Yeah, well, typically we consider the language models either like supervised models or self-supervised models, depending on the terminology. Basically, we assume that everything that is being learned by the language models that influences the weights of the neural networks is coming actually from the errors that these models are making at the output layer, and the errors have to be computed by actually having the gold standard, which can be, for example, the next word in a sentence. But that's basically supervised learning. Now, the idea of like more unsupervised learning would be that, like I believe that there should be some mechanisms that would allow the model to change even when there is no access to these error vectors, when there's not even possible, for example, to compute how the error vector should look like at the output layer. Like just to give an example, like there's this area of reinforcement learning where actually people are solving some problems, like for example making a bot that plays chess, and there you don't really have access to what is the perfect move that you should do next. In case of language, you can think of chatbots. You also, like, if you have a chatbot that is communicating with the user, there's no perfect solution what the chatbot should be saying at which context, because there's millions of possibilities. Of course, you can make some gold standard in some conversation, but this is not going to be practical if you expect that the chatbot will continue learning from a conversation with a user, not with a trainer, but with the user, that when it will be used in some online application. So just assume that you deliver some chatbots to users, and you expect that these chatbots should be learning, should be adding information to their memory. The user will say what is his favorite movie, or what he doesn't like, or what he likes, and you expect that a clever chatbot should remember this information, should store it somewhere in the model, either in the weights or the activations. Somewhere it should be stored, possibly in a persistent way, so it doesn't get erased. So that's what I would consider unsupervised learning, because you don't really expect that the user of the chatbot will also always correct the chatbot and tell him what he should have been doing, saying in which context. That doesn't make sense. You really need to rely on different mechanisms than the stochastic gradient descent as it is in supervised learning. So that's what I was talking about with this unsupervised learning, where you actually expect to be learning, for example, just by observing something, just from the inputs. The user says something, you should remember it, you should change the model should change itself somehow, but without access to any error vectors.
So just a quick comment, but you drew the distinction with learning chess where there's a clear success. The machine will either win the game of chess or not. What's your model for if you free a chatbot up? Other than people not using it or using it, is there any other error message you can imagine that a language model could learn from the chatbot?
I think that's interesting with the chess. So yes, you actually know that there's a success, but you only know it for sure when the game ends. So you need to do, for example, 30 moves, and then you are given this binary information. You did win or you did lose. You don't really learn much from this binary information. It's similar with chatbots. You can have a chatbot that holds a conversation with the person, and then at the end the person says, okay, I did enjoy this conversation, or I did not enjoy it. But that's just one binary information. You can't expect to learn basically the conversation just from this binary information at the end of the conversation. You really should assume that there should be some learning mechanisms, so that when the user says what is his favorite food or whatever, that will already trigger some change in the model, and not rely on this final judgment of the conversation by the user.
I have more questions online, but is there one in the hall?
I think, well, there are many questions here, but do we have time still? I think it's 4 actually. Really 4?
We've got 30 seconds.
We can? Okay, so one last. So we have Mark here. Question from... Okay, Honza is chair, so...
That's not why I said that there was 1 minute left. Well, thanks a lot, Tome, for excellent talk, and also I'm very proud of everything that you've achieved. My question is the relation of the data versus structured knowledge is my popular question. So basically, all the language models, whether n-grams or neurals, are learning on the sequences of words or symbols. While the mankind has basically developed lots of structured knowledge. Well, in the past it was the dictionaries, the penal codes, nowadays it might be the word nets and ontologies and stuff like this. And there are some people that say, well, you can forget about this, just pour in more sequential data and it will learn. And the others say, okay, well, this structured knowledge should be somehow used and distilled for these new language models. What is your opinion?
Yeah, that's another never-ending discussion. So just quickly, I think that it's totally valid if there are two conflicting opinions in the research community, and people should not hate each other for thinking differently. I was always on the side that all this explicitly defined knowledge is going to be unnecessary in the long term, and we should be aiming on having models that can learn actually from the data. So I would say that even models like Word2Vec can actually quite easily be used to generate a large noisy knowledge basis that will cover many more topics than for example WordNet. So in other words, you can generate a much bigger word net, also noisy, from even like language models. I was showing the examples with the question answering with the language models. You can take whatever big language model is available today, like a pre-trained one, and start asking this model, like, what is the capital city of whatever, or give me a list of countries, and then give me a capital city of this and this and this country. And this way, with just a very little amount of work, you can actually start generating large knowledge bases, and these are going to be quite good. Of course, there's going to be mistakes, but it's kind of like a knowledge derived from these general models that just learn pretty much everything, including what is often considered to be the mistake or like a missing part of these knowledge bases, and that's the common sense. Like you know, like if you start defining the knowledge in this explicit way that I described, like in WordNet, you will often miss like very, very trivial information that nobody bothers to actually enter in these WordNets, like that the dog has 4 legs or whatever. It can be actually missing there. Well, it's actually always like going to be present in the language model. So I think that not trying to define the knowledge explicitly, but relying on models that actually learn this knowledge on their own while optimizing some very general function like entropy. In my opinion, it's actually quite a bit better, and we will save a lot of work this way and even end up with better results in the long term. But again, as I said in the beginning, that's like my opinion, and I completely understand that there are other people in the research community who think that it's a great idea to actually build these explicit knowledge bases. So I think that as I was trying to say during the presentation, I think it's good to keep actually diversity in the research community and allow people to explore, especially the topics that don't really work well yet, because I often feel that the research community stresses too much the things that already work, that there's too many people working on what already works, and making incremental changes to it, because that's the easiest way how to get papers published and everything, publish or perish, right? But I think it will be good for making the research progress faster if there will be some incentives for people to even like explore things that are kind of like different than the standard ones.
So I think we really need to stop. It's actually 5 minutes late. Mark, so there are many questions actually here, and I think it's triggered many questions also here locally. But Tomáš, you are staying, right, for 2 hours, sure. At least 3 hours, so please find Tomáš, speak to him. And Mark, do you want to say last few words?
Well, no, all I can say is, Tomáš, thank you very much for a very interesting talk. Some great ideas there, and I would fully endorse your idea of diversity of ideas and communities, and it would be great if we were slightly less focused on just simply empirical performance gains.
Thanks.